All right. So today, all we're going to look at is section 9.4. We're going to be looking at doing hypothesis testing for what population mean when we know the standard deviation. On Thursday, we'll go through the situation where we don't know the standard deviation. So, but the process will be pretty similar in those two situations. So let's just go through what a one mean z test actually does, what we need to know, and how we go through and do it. So the three assumptions that are the most important is a simple random sample. We need to have a normal population or a large enough sample to do it. And in this situation, we need to know this standard deviation. So for the most point, we assume a simple random sample. And it was kind of funny because I was sitting there. I like Neil deGrasse Tyson, who's a national physicist. So he has a podcast called Star Talk. And last night, one of the conversation that I was listening to was actually about, like they were talking about how the concept of random sampling revolutionized the scientific method. Because once we were able to do that, we were no longer held to just your observations. So you were able to look at the testing and say, okay, I know this. What does this sample actually show me in terms of what should be happening or should not be happening? So that we take for granted in this situation because we're so used to just doing random samples that it's something that we didn't assume wasn't done at all points. All right. But random samples are important. So, and remember we talked about that at the very beginning of the class, that when we're having the random samples, it's got to be truly randomized. All right. It's not just picking certain people. You've got to have that random piece in there. A normal population or a large sample. What's the number for the large sample? 30, which sounds extremely small, but it's 30. All right. Or we know that it's a normalized population. All right. So step one, we need to look at the null hypothesis and the alternate hypothesis. The null hypothesis is what is known, and the alternate hypothesis is what we think is going on. So your alternate hypothesis can be one of three situations. It is not equal to the mean that's given. So I mean that it's vary in some way, but we're not sure which direction, or we just know that this is not correct. So that would be a two-tailed test. And then we have, it can either be less than the mean that's given, that'd be a left tail, or greater than the mean that's given, that'd be a right tail. So depending on which ones we're looking at, that varies how we're going to do the actual calculation at the end and determine our hypothesis. Okay. Any questions with that part? I think this part, as crazy as it sounds, is the most important piece of it, making sure you understand which one's your alternate, which one's your thing to be able to determine, because that makes everything else after it follow. All right. The second thing we need to do, we need to determine our significance level. So we were talking about it last time as like 95%, 99%. Significance level is actually the opposite of that. So a 95% would be a 5% significance level. A 99 would be a 1% significance level. So it's the same concept, just the opposite number. All right. So if you see a 5% significance level, in essence, we're looking for that 95% when we're looking at the z-table and stuff. We're going to compute the value of the test statistic, that's the z-score, and when we're looking at the other one, the t-score. So it's just the sample mean minus the mean of the population divided by my standard deviation divided by the sample size, the square root of the sample size. And that's going to be your z that we're going to be looking at. That's my test statistic. Once we've got that information, we have one of two methods. These are the two different methods that we looked at last Tuesday. We have the critical value approach. Critical value is looking at that Z. So if it's a two-tailed, we do the Z of the test statistic, or not test statistic, the significance level divided by 2. For the two-tailed, one-tailed, we look at the negative version or the positive version of that, depending on which direction we're going. If the test statistic falls within that rejection region, you can see the breakdown there. It's one of those regions. We reject it. Otherwise, we do not. So the critical values is looking at the Z-score, basically, and figuring out where that falls. The second method we looked at was the p-value approach. It's exactly the same thing. The only difference is this time we're looking at the percentage of it. All right. So when we're looking at, if we're looking at a 5% significance level and it falls at 0.4% or 4%, then we would reject it at that situation. So those are the things. We're either looking at the critical value, the Z-score, or the P, which is that percentage. Concept's exact same, breakdown's the same. It's whichever method you are more comfortable doing. All right, it doesn't make a difference. So on the test that I'm going to give you, I won't ask for a method. All right, you can use whichever method you want. So, and the vast majority of the questions are going to come from 9.4 and 9.5 because 9.1, 2, and 3 are basically telling you the process to do 9.4 and 9.5. So the vast majority of the questions on the test are going to basically be on like what we're doing today and on Thursday. Once you have that, we interpret the results. So if it falls in the rejection region, we will reject it. If it falls not in the rejection region, we could not reject it. Notice how you never say you accept. It's you reject or you cannot reject. Okay. Because we're not proving that something is true. We're just trying to say that it's either not true or we don't know, basically. All right. When you can do this. So if we have a small sample size, let's say less than 50, so 5, 10, all right, the only way you should use this is if you know it's normally distributed. Okay. So you want to make sure that the data is normally distributed if you really are looking at a very small sample size. If your sample size is between the 15 and the 30, because remember 30 is we don't have to worry about it, you can use it, again, as long as it's not very far from being normally distributed. So we'd have to look at and make sure that it's pretty close to being normally distributed and that there's no outliers that are going to totally throw off the data. If we have more than 30, we can use it without restrictions, except if there's outliers. So if there are some outliers, and we can't just justifiably remove them. So if you remember the situation we talked about last week was the chicken. Like we had one person who didn't eat chicken at all. It's like we could justifiably remove that because we're talking about people who eat chicken. All right. Or if we could justify it by there must have been some error in the actual data and we can remove it. That's fine. If you cannot remove it, what you want to do is you want to do the test twice. You want to do it with the outlier in it, and then you want to do it once without the outlier in it. And just see how it changed the conclusion. If the conclusion's the same either way, doesn't matter. If the conclusion changed, then maybe we need to look at a different method to do it. And there's other methods. We're not going to get to it in this class, but there are other methods to be able to do a lot of this stuff. If you are more interested in statistics after taking this class and you want to go on, there are higher level statistics classes that do go into those other methods and stuff. If the outliers are present but you can remove them, remove them. If you had exactly 30 data points and you removed an outlier and now you're at 29, now you got to, again, make sure that the data is normally distributed, because now your sample size is smaller. When you remove it, your sample size changes. So that's why a lot of times when people do, you want more data than you could use. So most people don't shoot for exactly 30. They shoot for a lot more than that. Any questions with those before we go into actually doing some problems? Yes.
Just a quick question
Yeah.
regarding the chapters 8 and 9 test.
Yeah.
Are we allowed to utilize a normal probability plot for on a computer for the test?
So any ones that I give you on the test, you're going to assume are normally distributed. You will not have to actually test to do that.
To remove outliers, I'm saying.
So,
If we wanted to ever get rid of
I'm-
outliers.
I'll tell you on Thursday, because I'm not sure if I'm going to throw an outlier on there yet or not. So, or if I throw an outlier on there, it'll be so obvious that it's an outlier that you'll not have to. You should not have to actually do a normal probability curve to do the test. Okay. So if you do, you could use your phone to do it. That's fine, because I'll let you use Desmos on your phone anyway, so that wouldn't be a problem. But I'm going to make sure most of the questions are normally distributed, so you don't have to worry about that part. Any other questions? Yes.
Is there a practice quiz?
Yeah, you missed that conversation. It's okay. I'll have it on Thursday. So
What practice quiz?
I give you the review test.
Oh.
Which I'll give you on Thursday. All right. All these problems that we're going to look at, we've seen before. Now we're just going to go through and do the entire method for you. So this actually was on your test. Half century ago, the average U.S. woman at her age 20s were 62.6 inches tall. The random sample of 25 of today's women in their 20s is presented. So they gave you the table. I didn't give you the table on here because I just don't have the room to put it on there, and I'm not going to make you do the calculations. On the test, you will have to do the calculations. So you'd have to, basically, the only thing you're going to have to do is find the mean of the data. So, and I actually very much put the mean on there so you don't accidentally mess up typing a number in your calculator. At the 1% significance level, so or in this response, the lower the significance level, the more accurate or the more precise your data wants to be. Okay, so if I did a 5% significance level, I'm going to be able to reject the mean a lot more because I have a bigger space to reject it. So 1%, it's even smaller. All right, so when you're looking at something that is important or that has some meaning and weight behind it, you want to use a lot smaller significance level. All right. If it's something that doesn't really make much difference, a bigger one's fine. So, and you can use smaller. You can go down to a 0.1% significance level. So it's like you don't necessarily, like we're making these simple with 1s and 5s and things like that, but you can go extremely small. Okay. And that's fine. At a 1% significance level, does the data provide significant evidence to conclude that the mean height of today's women in their 20s is greater than the mean height of the woman in their 20s a half century ago? All right, so we've got the mean of the population that we are assuming. We've got our standard deviation, we've got our sample size, and we've got our mean of the sample. Okay, so what's step one?
Dictate the null and alternative hypothesis.
Okay, so what is my null hypothesis for this?
That the mean height of the women in their 20s are 62.6 inches.
Okay, actually, I lied. What's the very first thing we have to do? We have to assume, we have to determine if we can even do this, right? So I know I said that I'm going to give them ones that we're going to actually assume to do, but we do want to make sure that look at this. So this was the normal plot curve. Notice there's no main difference. It is a normal breakdown. So we don't have to worry about that part in this case. All right. So
Wait, why did you lie? I'm confused about that.
no. I said on the test we're not going to have to do that, and I like that. That wasn't the very first thing you always want to make sure is that you can actually do the test before you actually go in and do the test. That was the thing. So now, step one, we want to find our null hypothesis and our alternate hypothesis. So what is my null hypothesis?
The mean height of today's women in their 20s is 62.6 inches. That's
Okay.
going to be our null hypothesis.
All right,
As for the
so that is 62.6. Okay. So what's my alternate hypothesis? What am I trying to show? Or what do I assume is true?
that the mean height of today's women in their 20s is greater than the mean height from half a century ago.
Okay, so my alternate is greater than my null.
Greater than 62.6.
Correct.
Right? Yeah.
So this is a what type of test?
One tail.
One tail test, and it's a right tail test, right? So it's right. Because we're looking at greater than. Okay. All right. So my all right, so you've got this information. And we're looking at a 1% significance. Okay. All right. What's the first thing we have to do? Or, sorry, second thing we have to do, because we've already done the first thing. Figured out a significance level. That's step 2, right? We got 1%. What's the third step? We got to figure out the test statistic, right? So that's my Z. So that is my sample mean minus my population mean divided by my standard deviation divided by the square root of the sample size. So I've got 64.24 minus 62.6 divided by 2.88 divided by the square root of 25. So this is not one that I would try to do on your regular calculator on your phone. I would use that for this. Because when you set this up, if you don't put parentheses in the right spots, you most likely are going to have the wrong answer. So the nice thing when you're using Desmos is it will show you exactly how you typed it in, so you know you typed it in correctly. So you can see how that's exactly as the formula looks. Okay. And we get 2.85. So the Z table always looks at 2 decimal places, so go to 2 decimal places for this. So 2.85. That's my Z. All right. So now we have our choice if we're going to do critical value or the p-value. So because it's a choice for you, I will do both. So my critical value, I have to find my Z that responds to the 1%. So you go to my Z table. And we're looking for, it's a one-tailed test, correct?
Yes.
So we're looking at the positive side and we're looking at 1%. Remember, the positive and negative is symmetric, right? So you could either look for 0.99 on the positive side, or you can just look for the 0.01 on the negative side and just change the sign. So if we look for, I find looking for the 0.01 a heck of a lot easier to do. So 0.01 is 2.33. Because 0.0099 is closer than 0.0102. So negative or 2.33 is going to be my critical value. So 2.85 is greater than the 2.33. So it's inside that. So 2.33 is right there. We're over in here. So we reject. Yes.
I have a meeting with my counselor.
Okay.
Sorry if I just come right back.
Yeah, that's fine. All right. So the p-value, we want to look at what the z-score is for as a percent. So 2.85. So we go down and look at the 2.85. 2.85 is 0.9978. So if we go back to my thing, I was looking for the 0.99 and 0.9978 over here. So I also reject. Thank you. So you can see how the two methods are basically the same process. They should come up to be the exact same response. If they don't, then you've done something wrong. Bless you.
Thank you.
I always wait for the second one because I know it's going to happen again. All right.
Wait, I'm done sneezing now.
So you don't have to do them both. You can use either one you want. So, because like I said, they will both come up to the same. I don't think either one is less work than the other ones. It's like they're basically the exact same amount of work. You still have to use the z-table. You're still looking for a piece of information. It just depends on which number you're looking for. You're either looking for the z to compare or you're looking for the p-value to compare. The most important part to this is you have to actually state in words what your conclusion is. Okay, so for this situation, we've rejected the null hypothesis. Okay, so since we rejected the null hypothesis, your assumption is that the heights for women today are higher than they were 20 years ago. Okay, that's what you would say. So it's not just reject, it's okay, we've rejected, what does that mean? And for this situation, that means my assumption that is that the heights of women today are higher than they were in the 1950s or half a century ago. So actually half a century, God, makes me feel old. So that would be 1970. And women in their 20s were born in the 2000s. All right. Any questions with that? Process sound good? Does it make sense? All right. Let's do it 2 more times. All right, a simple random sample of 18 adults with incomes below the poverty level gives a daily calcium intake shown at a 5% significance level. Does the data provide significant evidence to conclude that the mean calcium intake of all adults with incomes below poverty level is less than the recommended average intake of 1,000 milligrams? This is one reason why the school lunch program requires you to drink milk. Because which has been shown that especially people in the urban areas in poverty levels do not get enough calcium. And as my mother-in-law found out, not having this calcium can cause a lot of trouble later on in life, as she fell and broke her femur the other day. So now she's the $6 billion man with a titanium pole or a brace in her leg. So, all right. So the question is we have to do some data. We have to do our hypothesis test to see if this is true or not. All right, so a simple random sample of 18 adults. We've met the simple random sample level. We just have to see that it's normally distributed. In this case, it is. There's one that's a little low, but for the most part, this is pretty much a straight line. We're pretty close to it, so we'll assume that it's normally distributed. And we have our standard deviation. So we can do our z-test for this one. All right, so step one is to do what? Null hypothesis and my alternate hypothesis. So what's my null hypothesis for this one? That my mean is what? 1,000. Okay? And my alternate hypothesis is what? Yes, that my sample is going to be less than the null hypothesis. Okay, so what kind of test is this? This is a left tail. Okay, so we're going to be looking at those negative values in this situation. All right, second step. Find my significance level. What's my significance level for this one? Yes. Is 5%. It's not a fish, it's that funky looking A. All right. So, next step. We have to do that z-score, right? So we have 947.4 minus the 1,000 divided by the, what was the standard deviation, 188, divided by the square root of 18. In this case, we get negative 1.19. All right, so when we look at this, what do we have to do next? Yeah, critical value or p-value, right? All right, so in this case, my z was negative 1.19, and for 5%, gives me a z-score of negative 1.645. Okay, so if I look at my curve, the negative 1.645 is here. So I'm looking at over here, but my value is really over in here, right? So do not reject. Now, if I'm looking at my p-value, I'm looking for the p of these, the negative 1.19 is 0.1170. Or 11.70%. So if I'm looking at my sting, 5% is here, but my value is over here, so don't reject. So based on my sample, I cannot assume that the calcium levels are lower in this population. Notice the keyword in that is assume. That's like saying, because you can't say the calcium levels are not, because we don't know that for sure. If we took a larger sample, if we took a different sample, remember the sample size of 18 is small, but it's not insignificant. All right. Any other questions with that one? Okay. All right, so let's look at this one. So one common estimate of the mean top speed for cheetahs is 60 miles per hour. If we have a sample size of 35 cheetahs, we want to determine at a 5% significance level, does the data provide significant evidence to conclude that the mean top speed of all cheetahs differs from 60 miles per hour? All right, since we haven't done one with an outlier yet, we're going to look at one with an outlier. So if we look at this data here, you go through and look at your numbers, and that one kind of stands out. So that's kind of what would happen if I'm going to give you one with an outlier. It's going to look really weird compared to the rest of it. All right, so, and if we looked at the normal plot, you can see how it's out there. The rest of the data looks pretty good, like nice straight line, but that one doesn't. So that's one of those ones where it's like, okay, let's just eliminate that one. Now, in this situation, that one seems extremely high. I would reject it because I'm going to assume something was wrong with the data in that situation. Maybe the gun wasn't calibrated, a lot of different things. That was actually the joke for a while. If you got caught speeding on the highway, you go in and you ask them when you go to court. You ask for the calibration results and everything else for the guns because they have to calibrate them, and it's within a 5% significance level. So like, if it was outside of that area, then you'd say, well, something could be wrong. Doesn't work anymore because they don't necessarily always use the radar guns that do that. They use other methods to actually catch you speeding now. But that's the thing. It's like we're going to assume this one was so far out there that something was wrong with it. So we eliminate that one. Now, how many data points do I have? I have 34. Okay. So when we're looking for doing our calculation, we're going to look at it using 34 instead of 35. It's funny. They actually use the calculation still with 35, and they shouldn't have. Oh well. All right. So we're going to be able to do this test. What is my step one? Right. So my null hypothesis is that the mean is 60 miles per hour. And my alternate hypothesis is what? Huh? That is not 60, correct. That my is not. You can put not 60, it's fine. It doesn't make a difference. These are things that when I'm looking at the test, these are things that I would expect to see. I wouldn't need to see what your null hypothesis is. I need to see what your alternate hypothesis is. Okay. All right. So what's my significance level I'm looking at for this one? 5% significance level. Okay. All right. So now we can go through and do our calculations. So again, let's look for my Z. So I have 59.526 minus 60 over 3.2 divided by the square root of 34. And we get negative 0.86. So if we're looking for a 5% significance level, we just did this one actually. What was the 5% significance level? 1.645. So the negative 0.86 So we have the 1.645 here, the negative version of it. Oh, actually, probably did that one wrong. This is a two-tailed test. Which number am I really looking for? Remember, we have to take that and cut it in half. We're looking at 0.025. So 1.96.
Both positive and negative.
Yes. Yes. So we're going to look at our thing. So I got the 1.96, the negative one on that side, the 1.96 on this side. My negative 0.86 is in there. So don't reject. Because it's not. And now if we look at my, so I got the 2.5% there, the 97.5% there, my p-value, and we're looking at negative 0.86. So I look at that on my z-score table. 0.86 is 1949. So that's over in there. So again, don't reject. So there's not significant evidence to show that the mean is different than 60 miles per hour.
Did we remove the outlier when we did this, when we did these calculations,
Yeah, the mean had the outlier removed.
which was 75.3?
Yeah.
Was the outlier? correct?
Yeah, we removed that one. That's why I used 34 instead of 35.
Wait, we didn't even recalculate the sample mean.
I didn't, it was already given. I didn't have us do it. I didn't have us calculate the mean on any of them. I gave them to you. That was already calculated without that number in there. That they did correctly. All right, let's look into the situation. So a new car manufacturer claims that the typical car gets 26 miles per gallon. We think the gas mileage is less. Okay. They're always less than what they actually say they are. Because they do it in an ideal situation and not actually going out there and doing it. To test our suspicions, we perform the hypothesis test. So my null hypothesis is that the mean is 26. My alternate hypothesis is that the actual mean is less than 26. Okay. They take a random sample of 1,000 cars and find that the mean gas mileage is 25.9 miles per gallon. Assuming that the standard deviation 1.4, they find the test statistics negative 2.26, and that results in statistically significant at the 5% level. So at the 5% significance level, we reject the manufacturer's claim. So what are we rejecting? We rejected that it's actually 26, right? And based on our sample of 1,000 cars, we found that the gas mileage is what? 25.9. Okay. Is that big of a difference? Okay. So statistically, we would reject their claim. But practically, does it make a difference? No. Okay. And that's important. So one of the things that math likes to do is that there's one answer, right? There's an exact answer. And I said in statistics, it's that gray area. All right. So, yes, the data shows that we would reject the claim, that it's obviously wrong, but 25.9 isn't a big enough difference that I'm going to go after him for it. All right. If it was 25, that might make a bigger difference. But a tenth of a mile per gallon, it's not going to make much of a difference. This is why nobody complains that a gallon of gas costs you or 359.9 cents. Which the entire reason they did that was to make it look cheaper than it really was. It's like it makes no difference. It's like just do $3.60 instead of 359.9, and we're fine. But it's a psychological thing. All right. So one of the things that we're looking at is sometimes when you get your data, it's like you have to determine, okay, yes, this is mathematically correct, but in reality, it doesn't really make much of a difference. Okay, so that does actually come into play. All right. Let's do one more. This is the one you guys get to try. All right, let's try this one. If you have your book, it's 9.87 in the exercises. You could look at there. But All right. So based on the problem, my null hypothesis was 16.7. And the problem says we want to mean length of imprisonment in motor vehicle theft occurs offenders in Sydney differs from the national mean. It doesn't say it's greater, less than, it says differs. So that means it's not this or not equal to, that means it's a two-tailed test. That actually makes a very big difference in this situation. All right, because if you did it as a one-tailed test and said it was greater than, then you actually would reject. But in this situation, it's a two-tailed test at 5% significance level. So my Z was 17.68 minus the 16.7 divided by 6 over the square root of 100. So it's equal to 1.83 is my critical value. The 5% critical value, since I cut that in half, is 2.5 is plus or minus 1.96. And 1.83 falls in the do not reject region. So I would say that based on the statistical evidence, I would assume that it does not that much of a difference in it. Okay. That's what your questions on the test are going to look like, is similar like that. Okay. I'm going to try to put ones where you don't have to actually do out the calculations for mean and stuff like that, because I'm not really testing you at that point right now. I'm assuming you can find mean pretty easily. So, any questions?
Can you go back to that?
Yeah. So on Thursday, we'll be doing the same concept, except we won't know the standard deviation. So we'll be using the T tables instead of the V tables.
I'm just confused how we got for the N 100.
Oh, because it said the sample size was 100. It didn't put it in numbers. It says 100 randomly selected motor vehicle thefts.
Oh,
So sometimes it's not necessarily going to be a number in there you're pulling from. So don't always look for numbers. Good catch. All right. And that I will see you on Thursday.